All right, this says that we're streaming now, although there's nothing going yet. But if you can you try to click that link in Teams and um, see if it works.
Yeah, it's on stream starting today.
Yeah. Okay. Good. All right. I think we're ready. All right. Hi, everybody. Hopefully, I'll show up shortly. Do you have that going now? There's it in my show up? Okay, awesome. All right. Well, anyone else watching out there? Hello. Welcome to the first live stream of the semester. I have the YouTube chat here if you have questions and you want to ask questions, or you can also send messages on Teams and those will come up and I'll get those there also. So today we're going to talk about the process of science and kind of go through some of the readings and assignments from this first module. Depending on time, we might then pick this up again next time. We'll see how it goes. All right, so let me make myself smaller here. All right, so the first thing we want to do is talk a little bit about the process of science and define some of those terms. And those of you who are here, you can always jump in with questions and stuff too. We've now had a chance to do a couple science experiments in lab where you've worked with like both just following directions, but also having some experience with inquiry and like asking a question and trying to figure something out. So that's kind of what we're talking about when we talk about the process of science. When we get into the readings, we'll see there are some, actually, let's do that first because that makes sense. So let's jump over to our first reading, which is the Feynman reading. So just some background on this. Richard Feynman was a famous physicist, won the Nobel Prize for some of his work in physics. He worked on the Manhattan Project to develop nuclear weapons, which he wrote about afterwards quite a bit. And because of his kind of status as a famous scientist, he later in his career would give more popular talks about like general topics about science or just kind of his opinions. He was kind of a big celebrity. People would pay a lot of money to come see him talk. So this particular excerpt, this is from a book, but it's actually a transcription of a of something that of a talk that he gave. And can you tell, am I frozen?
Yeah.
Okay. Let me switch this and then switch it back again and see what. Nope, still frozen. Okay. Well, this seems to work, so I seem to be okay on this version. Hopefully the audio is coming through. I don't know. It's unfrozen, but I'm like in the middle of that, right? Right? Yeah, okay. So I can't make myself small. Well, okay. I'll just have to do it manually. Because I don't need to be giant in the middle of the screen here. Okay, Still unfrozen. Still good. Okay, great. All right. So anyway, so this is a transcript of a talk that he gave, and I think it does a nice job of talking about some of these questions of science. What is science? What does science do? What does science not do? If you haven't had a chance to read it, please read it. It's not real difficult reading. It's kind of an interesting talk, but I want to just point out a couple important pieces of it. So first, when we talk about what is science, I like that he splits it up here into three different things, and that's sometimes where this confusion comes from. That science is that word is used to mean three different things. One is a method of finding things out. So, like, you use the scientific method, you do science by asking these questions, by looking at evidence, by weighing evidence, things like that. And that is the scientific process, and that's science. Sometimes it means that it's the body of knowledge that you got out of things. So if you're in school and you're studying science, that means you're learning about all of this stuff that was found out using the scientific method. So that's like a second kind of definition of what science might be. Um, then the third thing is sometimes it's the new things you can do when you have found something out, or the actual doing of these new things, which he says we often call technology, which I think is correct. So sometimes when people think about science, they think about like how you can make computers or cure diseases or make things more energy efficient or alternative energy solutions, things like that. That again, those kind of all come from the scientific method, but it can be confusing when we say science and we're talking about one thing and someone else hears the word science and they're thinking about one of these other things. So he then goes through and kind of talks about what the impacts of these different areas of science are, these different ways of thinking about science are. So first of all, with technology, that's like the most obvious public way of doing science. Like we all use things, we all benefit from things that have been found out. But if you kind of think back of the number of steps that had to be taken for those things to come into effect, when somebody was first figuring out how atoms worked, they weren't really doing that with a particular application in mind. They weren't like, oh, we got to figure out how atoms work so that we can have computers. Like that wasn't really how it worked, right? Those are totally separate processes that build over time. And so now we see the technology, and so this is sometimes a mistake that we make. We think, oh, well, we can just study something and then figure out how to, and then use it to solve this technological problem. It doesn't always work like that. That you have to find something out using the scientific method that may or may not have a specific application. The other thing is that technology can be used for good or evil, which he talks about here, right? So like, for example, we like improved production, but we have problems with automation, like, AI writing your papers for you or whatever, but maybe that's also solving some important problems. A big one that Feynman himself wrestled with was the idea of nuclear power, that you have this extremely powerful energy source that's not a fossil fuel that could be used for all kinds of energy purposes, but then also can create these horrible weapons that he kind of was very concerned about for the rest of his life after he helped develop them. So a big theme of this paper is kind of wrestling with that, like what responsibility does doing science have to the moral aspect of the applications of whatever you're doing. So for example, and this guy was also kind of a storyteller and a guy who liked a bunch of people to listen to him. So you don't really know if the things he says are necessarily true, but he says he met this person, which he could totally just be making this thing up. And somebody said, to every man is given the key to the gates of heaven, the same key opens the gates of hell. I think personally that he made this up because it's a very good analogy for what he's talking about, that when you find out things about your world, when you find out science, you can use that for good things, and you can use that for bad things, kind of like the Spider-Man thing. And does the person who's finding out the concepts or understanding the world in the scientific way, do they have the responsibility to make sure that this is not used for bad, or do they have the responsibility to just not find it out in the first place because it might be used for bad? These are rhetorical questions. I don't know. These are things that we can talk about. To Feynman, it was pretty clear that for him, absolutely people should find out whatever they can find out, and it's a totally separate problem as to how to use that. I think he says in here. Um, that he's talking about nuclear power. Um, that this is not a scientific problem. He says this it's far more of a humanitarian problem. How to work the power is clear, but how to control it is not. And so that's what he says is basically a political problem. People have to figure out how to use this power. It's not the scientist's responsibility to not understand the power in the first place. And so that's an interesting thing that we can talk more about. Those of you who are here, I know it's not a lot of you, but if there were a lot of you, do you have any comments or like things that you would say to that idea of like? Yeah, it's true. But what if I mean, this to the same thing, to the same idea, like, okay, that's a pen, but like, if you were if you were, I don't know, if you had something that more clearly could be used for bad reasons, it's like more obviously, maybe even, I don't know, like, I don't know much about things, but
If the weight of the bad thing is more, like it's more easily used for the bad thing than the good thing, then just don't figure out a different way to do that good thing.
yeah.
If there's something with no practical application for anything good,
Mhm.
use for evil,
Sure.
someone will figure it out eventually anyway. So,
Yeah.
I might as well find it out and go, don't do this.
Yeah. Yeah. Yeah, I think that makes sense. Another version of this problem is like even thinking about stuff like careers. Like, if you go into, let's say, science and you want a job as doing science somewhere, okay, so let's say you really have like environmentalism is an important value for you. Okay, so clearly you're not going to like be the person at a chemical plant who's in charge of like dumping stuff in the river and covering it up, right? Because that's clearly against your values. But like, are you going to work for a company that happens to also like mine, do oil and gas mining and increase production of oil and gas, which is potentially increasing climate change, but it's like again a few steps removed from what you're doing. Like, how much responsibility do you personally have in thinking about how you're contributing to a problem versus are you just doing this science thing? What happens when it becomes a little bit more fuzzy?
Depends how strong your morals are. If you work for that company and you like clearly know what they're doing, you try to find a different job. And if you
Yeah.
can't find a different job, then your morals are compromised.
Yeah. Yeah. So that's something that we're gonna look at, I think, throughout the semester is this kind of like what is science just finding things out, or are we also concerned with the results and the consequences of finding those things out? So moving on with Feynman, so he kind of talks about this difficulty with technology. Um, and then he moves on to the second part of science, which is the contents, the things that have been found out. He says this is the yield, this is the gold, this is kind of like the overall body of knowledge. And this is also kind of what scares people about science in terms of like academically. Like if you've heard, oh, science classes are hard, I don't want to take science, because it's this big body of knowledge that you have to like get through somehow that could be really uh, difficult. It could be really I don't know, it's just a lot because it's been going on for years and years and years and years. You can also, he says, because he's talking to a popular audience here, so he's saying, do you think it's dull to like, study this stuff? Because a lot of people do, or think that it's difficult. Um, and so he kind of he goes into the story about kind of discovering the world, and he says, but see that the imagination of nature is far, far greater than the imagination of man. So, like, we can have all these stories about how our world came into existence, but to him, to Feynman, the actual, like, what is actually in nature and in the world is more amazing and beautiful and imaginative than anything humans have come up with to explain those things. And that for him, that's sort of part of that motivation, is discovering that beauty that goes behind our world. Um, so, and he describes it quite beautifully, so it's worth walking through that. Remember, of course, that this is his writing from his perspective. This is, this is not like a textbook. This is not meant to be something that is taken as fact for you. This is how he sees it. All right. So he goes through all these different things that he thinks are so beautiful that we've discovered as a result of science, physiology, electricity. Um, so then let's move over to the third one, which is this method of finding things out. And an important thing here that I've underlined is that the method is based on the principle that observation is the judge of whether something is so or not. So either you observe, and observation is defined very broadly here. So observation is not just seeing something with your eyes. It can also be, measuring something or whatever. But it's the idea that if you can measure something, then you can test it. And if you can test it over and over again, then you can come up with these kind of overall rules. But the important corollary to this is that if you cannot test something via observation, then it is not subject to this way of finding things out. And this is something that is in a lot of conflict all the time as people try to use the scientific method to investigate things that can't really be found out in this particular way because they can't be tested. So just as like kind of a silly example, you can't use I don't think he uses this example, but you can't use the scientific method to discover if you're in love with someone, right? Like that's not, because you can't like propose observation-based tests that then prove that or not, because all of the data, if you will, for that question is actually in your head. It's all coming from your own brain. So there's no like external observation. There's nothing that like where you and I could do the same tests and come up with the same answers the way that there is about what something is made of in the world. So questions like that are not really, like, the scientific method doesn't really go for them. And then there's, as you get kind of into realms where it's a little bit fuzzy, sometimes we can have some problems because, like, if you politics and economics is another area, where like the scientific method is often used to try to find things out, but because they're dealing with people and people's interactions, it's often not really appropriate because the data is like compromised basically from the beginning. So another thing with this is that he attempts to talk a little bit about this problem that we have in science, that we still have, which is, what does it mean for something to be proven scientifically? And what it does, what it means, which is what he talks about, is it really means to test something. So can you test it? Can you test it? Can you keep getting that result from that test? Which is different from like a popular way of saying prove, which means basically it is absolutely true and you cannot violate it. And the reason that becomes a conflict is that there's always this uncertainty in science because there's always more data that you could collect. There's always a more precise theory that could actually be correct. Whereas in other realms, like, no, this is true, this is proven, this is correct. So to go back into our other notes, one place where we get in trouble with this is with these terms law and theory. So let's take a second and define these. All right, these are some of the most difficult terms that we'll deal with this semester because they're also used in non-scientific contexts, and it's very easy to get those definitions confused. So let's straighten them out here. So in science, a law is pretty simple. It describes a set of observations. So for example, we have these things called gas laws, which describe how gases are affected by different properties. And one law says that when you increase the pressure on a gas, its volume decreases. So when you squeeze something with the gas in it, the space that it takes up goes down. And that is a law because it's a set of observations. Every time you do that, you see that effect. So it's that cause and effect relationship that just happens over and over again. But what that doesn't tell you is why it's happening. So for example, that same example, when you can, like, imagine you have a syringe and you hold one side shut, like you hold the end shut, and then you push the plunger with just air inside, and the amount of space the air takes up goes down, but the pressure increases. Now, if you fill that with water and you try that same thing, you can't do it. You can't squeeze the water or it will just come out. So the law says that this happens to gases, but it doesn't attempt to explain why. Like, why does this happen to gases and not liquids and not solids? What's special? What's actually going on? And so for science, the more important thing than the law is the theory, which describes why something happens.
Is it okay to say that it's been a set of consistent observations?
Sure, you can say it's consistent, yeah. And so that's kind of what also, since you say that, where some of this misconception comes up is a lot of people like to say a law is like absolute and unchangeable and fixed and known and proven, and a theory is like just an idea that you're not sure about, and that's not really right. They actually are different things in the scientific realm. But it is true that because a law is so simple, it's just observations, that it usually is pretty much true because you just keep seeing those observations. But there are some exceptions. I mean, laws are subject to evidence. They have to be proven. They can be disproven. Good example of that is you've got Newton's laws of motion, which describe, how things fall and how things fly. And I don't know if you studied that kind of stuff in physics before, but you can, like, Newton's laws are very powerful. You can, figure out if you shoot something at this angle, at this speed, exactly where it's going to land, right? But Newton's laws don't work in some situations. So for example, in the 20th century, it was discovered that the laws break down when you get to really small things like atoms and electrons that are moving fast. And when you get to really big things like planets and things, you have to take some other factors into account. Relativity comes into play there. So it's not that Newton's laws were wrong, but more evidence came out that showed that they weren't absolute in all circumstances and that we actually need new ways of describing what's going on with other things. So in science, what we're usually more interested in is the theory. Can we come up with a coherent explanation that can be tested that actually shows why these things are happening? And just as an example, I'd like to give the example of atomic theory, which is, spelled wrong, which is the theory that matter is made of atoms, that there are these small, like, irreducible particles that I wouldn't say that's a controversial theory, right? Like, most people believe that stuff is made of atoms. It's as well settled as anything could possibly be, but that doesn't make it something other than a theory. It's still a theory because it explains why matter interacts in the way that it does. Because if we assume that there's these atoms, then we can explain all these other things. And we can test that theory by basically the entire field of chemistry tests that theory when we put things together and try to, create things. So try to break that misconception in your brain that a theory is somehow less true or less correct than a law. In science, they refer to different things and different processes. Right? They both need evidence. They can both be disproven with enough evidence for something else. And so going back to Feynman, Um, where am I? What am I looking for here? All right, so here he talks about there's another number of special techniques associated with what science, what he calls the game of making observations, um, and like how to interpret those results. So, uh, for his example, he says there's a famous joke about a man who complains to a friend of a mysterious phenomenon: the white horses on his farm eat more than the black horses. He worries about this and can't understand it until his friend suggests that maybe he has more white horses than black ones. Right? So like this sort of thing happens with science all the time where somebody comes up with some kind of a result and especially if it's an exciting result, it gets amplified in the news media and social media, and suddenly nobody's eating whatever anymore, like oh, we can't eat almonds anymore because they came up with this thing and says don't eat so but then when you actually look into the data, it's really not that clear, and there's actually these other problems. So one of the things that I have linked in the module is a podcast episode where they speak to exactly this, this idea of these things that are sciency, but they're really doing it the wrong way. And there's some special names for it, like p hacking. What's the other one? Parking, yeah, where you're basically you have a data set and you're figuring out something. You're like pulling things out of the data after you get the data, instead of saying I want to see if this is true and then testing it using data. And so this is what Feynman's saying here as well. Like these kinds of like mistakes in judgment. Oh, my sister had a cold, and in 2 weeks, because she took whatever. For example, vitamin C. Vitamin C has been uh, over and over and over again. It's been disproven that vitamin C, that like extra vitamin C helps with anything, but people will still take their vitamin C and be like, yeah, I had a cold and I took my vitamin C and it got better, and so I always take vitamin C when I get a cold now. Um, Even though when you actually subject that to tests, it totally breaks down and doesn't work. Um, okay, so let's see, how are we doing on time here? So I don't want to go too much longer. So you can read through this. I think it's really interesting and worth your time. The next reading, I don't, where is it? Here. This one, from Science for All Americans, is not as interesting of reading, and you maybe don't want to go through it quite as carefully. But this is more of a textbook type thing if you want to know what um, more specifics about the definitions of these terms, right? So science saying that things occur in consistent patterns, that they are comprehensible. A lot of times we don't think about the assumptions behind what we're doing, but they are assumptions. Like we assume that everything is a vast single system where the basic rules are the same everywhere. And so far that seems true, but we don't actually know that because we haven't investigated everything everywhere. So there are some assumptions that underlie this stuff. And there's also, like we talked about in the last article, there are questions that aren't really subject to scientific inquiry because they don't fit in these types of things. Education is another one, where we talk about things occurring in consistent patterns that are comprehensible through careful systematic studies. There's lots of people using the scientific method to decide, to figure out like what types of techniques work best to educate students. But there's so many variables because all people are different that it becomes really difficult or impossible to actually carefully, systematically control studies involving people like that. And so there's a whole question of like, is this whole thing even subject to scientific inquiry or not, or is it something totally different? So if you want a more like drier but more less personal type version of definitions of these things, I think that's what this particular paper does pretty well. So it's worth it to look at that. Okay, and then the last thing, I didn't copy it here, but I'll jump back over to Teams so we can take a look here. Oh yeah, when I do it on my tablet here, it always doesn't always look nice. Let's see if I can just bring it up here. So there's a really interesting textbook that, let's see if it comes up, that was written a few years ago called Knowing Home, Braiding Indigenous Science with Western Science. And it's really a philosophy, it's really a branch of philosophy called Science and Technology Studies, which is like thinking about these assumptions that we talked about. What does it really mean? Like where does the scientific method break down? What does it really mean to do scientific inquiry? What kinds of assumptions are true? What kinds are not? And so these people work kind of in that field, and they have written a lot over the years comparing other ways of knowing things that are non-scientific but are also not wrong. So there's a difference between a inquiry or a way of knowing something that is not correct, like we talked about, like p-hacking or whatever, misapplications of the scientific method. There's a difference between that and just a different way of knowing things. So there's other ways of getting knowledge besides the scientific method. Before the scientific method, well, if you look at way before, you can look at indigenous techniques, which many of them are very similar to science. They certainly made observations and understood their world in a similar way to the scientific method. But they also relied on things like stories and oral tradition and other ways of communicating knowledge besides the scientific method. And then if you look after that, in Western societies in Europe, you look at what I would say is probably a less good way of knowing things, which is like more based on authority. Like the king would decide what was true, and then everybody had to believe that's what was true because that's what the king said, and then like that's how you got knowledge. It doesn't mean everything was wrong, but that's a different way of getting knowledge. Right? Getting it from your parents, getting it from authority is a different way than finding it out yourself, or even culturally finding it out from other people that all sort of believe the same thing. So there's a lot of stuff, and this book is geared more toward educators, but this particular chapter just kind of talks a little bit about what does it mean to learn things in um, in a way that might be considered indigenous science or indigenous knowledge, and how is that different from the Western scientific method. So, for example, they outline 6 principles that kind of talk about what is the nature of science from the indigenous worldview. And so you can think about how those work with what you've learned from the Western science worldview and how there are some real similarities and then also some differences, but how other people can understand their world and how that's sort of like a general, it seems to be a general feature of humanity, is just like the desire to understand our world. And so you can see these principles: place-based knowledge, multiple perspectives, living conscious universe, focus on balance and harmony, cycles and circles, interactive and reciprocal relationships. So you can see some examples from that and where that learning comes from. And then since we're all more trained in the Western method, we can see how there are advantages and disadvantages to these different ways of knowing things. And so as you're thinking about this, one thing you might want to do for this module is just do some writing or some talking if you're more of a talker, record yourself or something, of just like your thoughts on these ideas and how you put these together and how these make sense to you. And then that's something we'll talk about at the at those midterm or those module 1 assessments, not this coming week, but the following week. So we'll meet together and talk a little bit more about this. So then next week we'll start module 2, and I will let you know when I'm going to do this, but probably it'll be Tuesday and Wednesday, where we'll talk about the material for the module in the same way. So do anybody who's here or online, have any questions or other things you want to go over? I would still recommend doing it because you got to be working on the other stuff by then anyway, just so it's done. But yeah, more important just that it's done before we meet. I would still do it, at least most of it now, just so that it's done, and then you can focus on the next module next week. Yeah. Anything else? Anybody online? I don't see anything. So, all right. We'll see you all next week.